There we go. Hello. Okay, perfect. So it's working. We're going to jump right into it. So this is going to be for going over the midterm. We're looking at some of the beginning chapters for biochemistry and make sure all my screens are up. Okay, so let's take a moment and look at these two. So a little bit so you can see it. Give you 90 seconds to take a look at these two and we'll go over it, okay? Okay, so the first question, it says, what does the Michaelis constant Km represent in Michaelis-Menten equation? So let's pull this up real quick. This out of the way. Let's see, take a look at what this is the equation right here. Vmax substrate over Km plus substrate. But this is what we're looking at for the Michaelis-Menten equation. This is the graph as well. So you'll see Vmax right here. I'm sorry, Vmax is up right here at the top. Km is decided by half of Vmax. Okay, so you see substrate concentration, which is located as A, and then the reaction rate will be right here. Okay, on the y-axis. Okay, so what does the Michaelis constant Km? Km is right here. Represent in a Michaelis-Menten equation. So in that equation, does it um, represent the maximum velocity achieved by an enzyme when fully saturated? No, it's not going to be the maximum velocity. And we see right here, just in this picture, Km is 0.5. So if this is half, this is full. It's not going to be full. So cross this one out right here. That's not right. Let's look at B. The substrate concentration at which the reaction rate is half the maximum Vmax. That sounds about right. So we'll leave it at B. Here, I would just mark it as B and move on, but just so we can learn, let's take a look at C. The amount of enzyme required to convert all substrate to product in 1 second. Okay, this one is a little bit extreme. In 1 second, not really given a time with this question. Required to convert all substrate? No. Okay. That's not the answer. So the answer here would be B. Okay, boom. Okay, next one, we'll leave it here. Okay, next one, you can still see it here. Okay, what is the significance of the enzyme substrate complex in the Michaelis-Menten model of enzyme kinetics? Okay, take a second to look at that. Okay, we have our answers. Okay, the enzyme substrate complex. So let's look at that real quick and we'll compare it to the Michaelis-Menten. Okay, remember the enzyme substrate complex, there is a, let's see if we can find a picture here. Okay, like this one. This one a little bit better. So it shows enzyme and substrate. The substrate is binding, so enzyme substrate. There's a catalytic step, which is known as K2. This is only a forward reaction, okay? Then it goes to enzyme and product, okay? So just one more time. Enzyme plus substrate. The substrate binds, okay? So they're no longer by themselves. They're together. This could be a forward and a reverse reaction, okay? But once the enzyme substrate has their catalytic step, K2 forms over here, okay? Non-reversible. Okay, so let's see if we can look at this and figure this out. What is the significance of the ES complex in the Michaelis-Menten model? Okay, so we see this here. This is just a temporary step, okay, right before we create the product. So we can go here and we could keep that in mind while we're looking for the answers, okay? It is a permanent bond that prevents enzyme reuse once a reaction occurs. Okay, already I don't like that answer. but we can figure out this is not a permanent bond, prevents enzyme reuse. Enzymes usually can be reused, okay? So that's not the answer. Let's see, it's a temporary intermediate essential for the substrate to be converted into product. Yeah, exactly. That's exactly what we were talking about. This is before the catalytic step. This is just happening here. Remember, I could go forward and I could go reverse. Okay, before it can be converted into the product. See, boom, right here. Okay, and I would just mark that as B and just move on. But we'll look at C and we'll explain why it's on C. Okay, so it represents the inactive form of the enzyme before the substrate binds. Once again, not true. They're binding. They're together. Okay, remember substrate binding. Okay, boom, boom. Substrate binding is here. Okay. Let's go to these two. Give you a couple seconds, then we'll jump right into it. Okay, pause the video if you need to. Get a celebrity right here, a celebrity dog. Okay. Here's question number 3. So if we have a tightly packed fatty acid, it could form more what kind of interactions? Okay. Um, and then also that would increase the stability of the molecule. Okay. This blank, the melting temperature. Okay. So right away, we're going to look at the answers. A, hydrogen lowers. B, van der Waals raises. C, ionic lowers. Okay, so this we're seeing as lowers, lowers, and raises. Okay, so let's just say I didn't know what van der Waals interactions were. Okay, and let's just say that I didn't know what hydrogen bonds or ionic bonds were. Okay, by a tightly packed fatty acid, it can form more blank interactions. Let's say we don't know that first one, but it'll increase the stability of the molecule. Okay, so if we increase the stability of the molecule, will that raise the melting temperature or will that lower the melting temperature? In this case, if we form more van der Waals interactions, which I'll show you in a moment, that will raise the melting temperature. So immediately we know that we're going to raise the melting temperature. You can cross out A, cross out B, and just move on. But let's take a look at van der Waals interactions. I like to call them the Tinder reactions. Reason being is that they're just a temporary step. Let's see if we can just get a quick picture so you can visualize this. Okay, it's just something that's just more so temporary, right? They meet up, they hang out, but these atoms, they're in this van der Waals force, we see that there's an attraction, right? And as this attraction happens, this positive side is pulled here, right? So this got the negatives and positives outside. So it's got the electrons on the outside, protons on the inside. That's what those negatives and positives are. Okay, so each atom is going to have that. The atoms are polarized. Okay, so we see that. So that causes an attraction. The negative electrons are going to be pulled to this side. The positive is going to be pulled here. Okay. Van der Waals forces, van der Waals interactions, they're great for biochemical processes in the metabolic system. That's because they can break easily, right? So if we raise the temperature, we increase the stability. Let's jump to the next one. Okay, give you a couple seconds for this one. But the question says, how can you protect hydrophobic side chains of the main chain from interacting with water? Okay, let's try to visualize this. So how can you protect the hydrophobic, so it means it does not like water, the side chains of the main chain from interacting with water? Okay. Hydrophobicity means that it doesn't want to be around water. So if the outside is water, the inside is not water, isn't it going to want to pack inside and stay away from the outside? Okay. I don't need to draw this, but I would just think of a circle. The outside is water. Everything's not going to want to be near the end because it's afraid of it. Phobic meaning fear. Hydra meaning water fearing. Okay. The side chains, meaning they're going to be close to each other. They want to pack inside the middle. So we're going to be looking for an answer that's going to reflect that. Now, is it going to expose them on the protein's outer surface to increase polarity? No, no, that's the complete opposite of what we're going to want to do. So we can cross that one out. B says chemically modify them to make them hydrophilic. It's a bit extreme, and no, I wouldn't even justify that answer. C, just mark it as C and move on. But let's look at the reasoning. So bury them in the interior of the protein away from the water, which is exactly what we're looking to do. Okay, so let's see if we can um, show you this. Show you a picture of this. Perfect, perfect. Okay, so this one, hopefully you can see. So here, they're going to want to well, actually, this kind of makes it a little bit better because there's colors. Okay, so red, hydrophobic, blue, hydrophilic, and then this black portion is neutral. So what it's going to want to do is it's going to want to compact and pack and pack and pack. So this is just going to want to keep burying and burying and burying and burying. So let's see if we can find another one. Um, my first time seeing this picture, so let me check. No, it's not do check. Can we get this? Can you guys see that? It looks big on my side of the screen. Okay, well now I can read it. Okay, so let's see what it says. So DH is a side chain that is a hydrogen bond donor. Yeah, okay, so they donate. A is a side chain that is a hydrogen bond acceptor. Yep, okay. We're going to go over that in a little bit. That's the next section we're going to go over. Okay. Um, uh, let's see. Gray hexagons are benzene rings. Okay, benzene rings. And then the red circled negative is charged side chain. Charged side chain. We're going to go over a portion of this in a little bit as well. So this whole picture that we just found, um, mainly talking about there's positive side chains. So you could think of Herc. I think of Herc like Hercules. So when it's protonated, it's going to be positive. Okay. I'm sorry, deprotonated. It's going to be positive. So those would be histidine, arginine, and lysine, HRK. And then these negative ones, DE, which we'll learn about in a little bit, they can have a positive and a negative charge together. So they can, yeah, we'll go over that in a little bit. But in this picture, you can see that. But with this, the inside, all these areas right here, they're going to be hydrophilic. I'm sorry, hydrophobic. And the outside's going to be hydrophilic. Okay. So when this protein is in here, it's going to have the water on the outside. It's going to want to slowly want to form in here. So find a better picture. Just something simple. Yeah, there you go. Something simple. I always like to keep it simple. Um, and this is also going to go over the delta G, delta H, delta S. Remember that delta G negative means that it's going to be spontaneous. Okay? Delta G positive means that it's going to be non-spontaneous. So it means it needs to have some kind of it's going to go against the natural flow of what it wants to do. Okay, so if there's delta G that's negative, this is how our body wants to have. These two yellow things are going to be, you can think of them as hydrophobic in this case, because they are. They don't want to be around water. Water's around them, so they're going to form together. And when this portion that it doesn't want to be in water is first dropped in here, see how water is going to form all around it. That's where it's going to be a non-spontaneous reaction. Okay, so we're going to see a positive delta G. Delta H is going to be negative. Delta S is going to be negative. And this is going to be, because this is pretty much a negative plus a negative, positive. Okay. Now, the reason for this is that the water is going to form around it. But then when another hydrophobic portion is put in here, they're going to want to form together. So they're going to be here and they're going to want to form together. And now we're going to see these water molecules form all the way around them. Okay. So now it's going to be more of a spontaneous reaction. Where's the delta H turn positive, delta S turn positive. Okay. And if we're not sure on the Gibbs free, here we go. And see, so this, if this was a positive number, and this is a positive number, so positive times a positive equals 0, okay? It's going to depend on what the temperature is. And let's see, actually, they have a better picture here. So if we have delta H, that's going to be positive. Delta S, that's going to be positive. But we're going to have a high temperature, okay? That means delta G is going to be negative, okay? This high temperature is going to be able to hold off. Now, but if this delta H is going to be positive, this delta S is going to be negative of any temperature, this would be positive. Okay, this is definitely something I would try to remember. Delta G, very important. So I'll put this in here for you guys. Bury this in here for you. There we go. Now we have it there. Okay, so question number 5. Take a second to look at it. Okay, now we're getting into the primary structures. Okay, what happens with the primary structure? Okay, so we want to be thinking about that. What happens with primary structure? This is a very simple question. Also a tip for when you're, excuse me, also a tip when you're looking at questions. You want to break them down if they're confusing. Like this one prior to how can you protect the hydrophobic side chains? I would more so think, okay, how can you protect them? What are they wanting to do, these hydrophobic side chains? What are they wanting to do when they interact with water? So, if you have a tightly packed fatty acid, it could form more interactions. I would think of if a fatty acid is tightly packed, will that increase the stability of the molecule if we do what to the temperature? I would try and combine both of these into one. Okay. The ES complex does what? CAM represents on a graph represents what? Just try to make it just simple. Okay. That way you don't have to take too much time. And then some of these questions they try to trick you. Not these specific ones, but usually. Okay. So in a primary structure, okay, we can think of a long chain of a covalently linked amino acids. Okay, they're linked between a peptide bond. Okay, so before we get into that, we want to make sure that we understand what that looks like. Okay. Oops, I haven't read the first time. Yay, here we go. It's a great picture. Oh, actually, this is kind of good. Okay, so you see there's an N terminus, a C terminus, there's amino acids. Can you see that? Working in here? Oh, there it is. Okay. So you see leucine, and we'll see cysteine on the other side. These are what these amino acids look like in here. It doesn't matter for this exact scenario, but this is just to get the picture. So it'll be a long chain of covalently linked amino. That's covalently linked amino acids via peptide bonds. So between each one of them, there's a peptide bond. Take a moment and try and remember, what is a peptide bond? Okay. What happens in a peptide bond? Okay. It's a great picture. It's all another good picture as well, so we might have that one too. Okay, so this is amino acid. So it's an OH group and then an H group. What they're going to do is they're going to form water. Okay. Get another picture. Okay, separate amino acid, separate amino 2. They're going to form via a peptide bond, form with water. So there's going to be this OH group, this H group is going to be plucked off. See how this carbon and this nitrogen are going to be bonded here. Okay, so this and this are still here, but they're just bonded. Pluck, pluck, boom, dipeptide, done. Okay, make sense? Got it? Okay, boom. So now we have that in mind. Is that going to involve a hydrogen bond? Mm, well, no. There's a carbon that's bonding to a nitrogen. Okay, is that a hydrogen bond? No. Okay, well, we're also plucking off of water, so that's not it. And also it says between backbones. No, that's not wrong. That's not right. So the sequence of amino acids linked by peptide bonds. That sounds correct. 3D folding stabilized by R groups. Okay, we're not, there's no 3D in here yet. We're just creating a long chain. So answer's B, move on. Okay. Secondary. Okay, ooh, now we're talking about a 3D again. I see that already. About local folding, talking about multiple polypeptide chains. So what is a secondary structure? Well, it's going to have a hydrogen bond between the atoms of their backbone. Okay, so that was really this first answer right here. So we're going to look for this first answer somewhere over here. Okay. So overall 3D structure of protein formed by R group interactions. Is it local folding, alpha helix, beta sheet, maintained by backbone, hydrogen bonds? Yep. I love that answer right here. Boom. I would just pick this and move on. But we'll find out why it's alpha helix and beta sheet, beta pleated sheets in a moment. Multiple polypeptide chains forming a complex protein. Oh, okay. Well, that's going to hint at our question down here. So you can just put that in the memory bank that multiple polypeptide chains forming a complex protein is probably a quaternary. Maybe it's a tertiary. We'll see. Okay, so the overall 3D shape of a protein is not formed by R groups, and that's not the secondary structure of a protein. So let's see if we can find secondary structure, and we'll look for those. We'll look for these. Oh, perfect. There's a little bit more detail. I like this. Okay, is the picture popping up? I guess it's not popping up. Oh, maybe I clicked on it too much. Okay, so this is the alpha helix and the beta pleated sheets. So pleated, think of that. Think of for some reason I think of jeans being pleated. I don't know if they do that anymore, but that was kind of big with Levi's at one point. They would have or Dockers. They would have pleated like golf slacks you could have. This is what these little pleats are. Okay, in between in between is going to be these hydrogen bonds. Okay, and that's going to create a beta pleated sheet. And alpha helix, it means it's just going to be going around and around and around and around. Okay, still going to have hydrogen bonding. So that is going to create this shape of the protein, right? That's going to create the shape. And also remember that these that prolines could be involved in here. We're not going to go over that right now, though. Okay. Tertiary. What makes the tertiary? Think about it for a second. Okay. So if we had the backbone have hydrogen bonds, we had the amino acids that created peptide bonds by removal of a water of H2O. What's the next thing that could possibly happen? So how can we combine two of those together? That's what I'll be looking at when I'm looking into this question. Okay, so is the overall 3D shape stabilized by an R group and backbone interactions? So this would be hydrophobic, ionic, H bonds, disulfides. I'm liking this answer. I really am. These are non-covalent interactions. Okay, hydrophobic, ionic, H bonds, disulfide. Okay. Remember, we go up to here. Covalent would mean the amino to amino to amino to amino. Hydrophobic, ionic, H bonds, disulfide. That's not what that is. Okay. Those are non-covalent bonds. Okay. Or interactions. Excuse me. Okay. And then this would be the overall 3D shape stabilized. I like that word by the R group and backbone interaction. So R group would be that portion of the amino acid that makes it the amino acid. Okay. Like that answer, but let's see what else we got. Sequence of amino acids forming peptide bonds. No, that was already the first primary structure. A regular repeating alpha pleated, alpha helix and beta sheet regions. No, not at all. Okay, so let's see a tertiary structure. Um, there's this picture here. This one looks fine. If it happens. Okay, so we can see hydrophobic interactions. Okay, we can see hydrogen bonds. We see disulfide bonds. We can see ionic bonds. So we can see all kinds of different things are happening within this polypeptide backbone. This would be this dark purple region. Okay. You see, I don't think I saw disulfide. Was there disulfide? Yeah. So this will happen between two cysteine amino acids. Okay. So they'll form a disulfide bridge. Okay. Very important. Super high yield. Okay. Tertiary, B. Let's move on. Quaternary. Okay. What we've seen, this is a little bit more rare than you would think. Quaternary. Um, what we'll do is we'll jump to this one and look right at the answers and see if there's something here that we've already gotten because we've already answered primary, secondary, tertiary. Let's see if one of them is already in here so we can immediately eliminate them. Okay, structure formed when polypeptide chains associate. Okay, polypeptide chains associate to make one functional protein. Ooh. Okay. Maybe. Individual amino acid sequence before folding occurs. We already saw that folding happened. Okay. It was right here. Random coil regions. Okay. Nothing of this is going to be random. Okay. Single polypeptide. No, this would be multiple polypeptides. Boom. We move on. Okay. Let's find out why it would be structure A. Okay. A coordinate structure. Okay. So we see that there's this. A simple way to think of it is that primary structure is just amino acids. Secondary structures when they either start having these beta pleated sheets or the alpha helix. So kind of like DNA, flipping, 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 flipping. So that's the alpha helix. Tertiary is when it starts to fold. And quaternary is when they have a bunch of these tertiary structures and they start folding into each other. Okay, and you get this kind of stuff. Okay, you can see there's a heme group in here. Oh, this is perfect. I like this. See, there's a heme group in here, and this creates a hemoglobin molecule. Okay, globin peptide, beta globin peptide, polypeptides. I'm sorry, globin peptides, globin, oh, globin polypeptide, globin polypeptides. Took three times, right? So there's one, two, three, four of them. Okay, and they all bond together. They're all together, and they create this molecule. Wonderful. Okay, so structure form of multiple polypeptides. See that? Move on. Let's go. Okay, next section. I have a few more questions we can go over, but I think let's go right into some content review, and then we can go over some questions if we have some time later. Okay. Water ionizes to a small extent. Okay, so Kw is going to equal to H plus OH, and this is a constant 1 times 10 to the negative 14th moles squared. Okay, that's the ion product constant for water. It's always going to be the same at at a given temperature. And so if one concentration goes up, we're going to notice that one's going to go down because think about it. Let's say this is 100 and then it goes to 1,000, right? Or it goes to 10,000. This number is going to have to change. Otherwise, this is going to be different. Or we could put it simply, if they're both 1, we change this to 2, we should change that, right? Because if 1 and 1, if Kw equals 2, we increase the protons by 1, so now it's 2. Kw is not going to be 3 all of a sudden. It can be, but to get the same, it has to be reduced. Okay, that makes sense. The pH of any solution is defined as pH log. Okay, so let's look at this. What's the point of knowing this? This is just showing you that the value of 7 as neutral pH is not arbitrary. So that's the absolute value of an ion, 25 Celsius. Yeah, 10 minutes left. 25 Celsius is between 0 and 14. And let's try to remember this last part. Huge. pH plus pOH is 14. Okay. Also, they're inversely related. Okay. So one concentration goes up, the other concentration must go down. Okay. Let's see here. Excuse me. So acids having different tendencies to ionize. Okay. Before we go into this, there are amino acids that ionize. There are some that do not. Okay. Now, if we look at the acids, we can determine if there's a weak acid that will dissociate in its environment. We can find weak acids, weak bases. acetic acid, carbonic acid, phosphoric acid. And we could see their equilibrium. Okay, so HA forward and backwards. That's what this means. This means H plus plus A minus. Okay, that's where you get the equilibrium constant, Ka HA over H times A over HA. Okay, in this case, we want to remember that if there's a larger Ka here, that's going to mean there's lots of dissociation with the strong acids. Okay, now if this number is lower or it decreases, you'll notice that it's a smaller, it's a weak acid because it's going to have a little dissociation. Okay, so we can think carbonic acid H2CO, H2CO3. It's in our blood. It's our main blood pH. Okay, we can see that via the bicarbonate buffer system, right? Phosphoric acid H3PO4. That's involved in phosphorylation, energy storage as well. Then we have histidine. What else we got? Let's say glutamine. They can act as weak acids, weak bases. Okay, in enzyme catalysis. So in a histidine, it can act as a weak. Let me reframe it. It can act as a weak base or weak acid in enzyme catalysis. So let's look this up real quick. Okay, so you can see here, there's a histidine, right? You can tell because there's two nitrogens. Yep. So I have a hydrogen bond, hydrogen bond. Okay, can act as a weak acid or a weak base. Boom, makes sense. Enzymes, got it. Okay, let's jump right to here. Conjugate acids. I'm sorry, conjugate acid base pairs in biochem. Um, like I was saying earlier, there are many amino acids that can ionize. I'll get you guys a list in a little bit, but here you can even see this picture. May not be that great of a picture. You can't really see, it's a little blurry. Okay, so we can see as the pH increases, we can see how there's changes in the environment. We can see this one's glycine, right? There's a carbonyl group. There's diprotic acids. There's a carbonyl acid. Um, what is the point of knowing all this? Pretty much it's letting us know that each acid has a conjugate base. Okay, so when an acid donates a proton, it becomes a conjugate base. So take a moment to think that when an acid donates a proton, so it's an H plus group, it becomes a conjugate base. Think of acetic acid into acetate. Okay, it means it's going to donate a proton, an H plus. The pH is going to tell us the pH where half the molecules are ionized. Okay, so if we have the pH below the pKa, we're going to have a more protonated form, more acidic. But if it's above the pKa, it's be more deprotonated. Okay, more basic. That's something I wanted to drive through here. I can't recall. So I want to get through a few more of these things. The conjugate acid base. Think about it as like the carbonic acid. So we got the carbonic acids, right? We're talking about up here. You got bicarbonate, phosphoric acid. They act as neutral buffers to maintain 7.4 pH, which is your physiological pH. Okay, which we'll see right here. So in this example, it's not but different. So this will be here as a buffer. So we see that this is just under 6. This is 5.76. This is just under, yeah, just under 4. So this is 3.7. So this range, see how it's a 2-point range? They do that so it just doesn't jump from one to the next. Okay? That's what these titration curves do. So a buffer, the question here says, it's going to answer for you. Think about it for a moment. So if a buffer if buffer doesn't resist change, what happens? I don't like the word about it. If the buffer doesn't resist change, what would happen? Think about it like that. The molecule would change, it won't change sufficiently, which is why there's a buffer range. Okay. So right in the middle, that's where pH is going to equal pKa. Okay, see right here. Boom. Okay. When it moves up, it's not. When it moves down, it's not. That's when the acids and the bases are in equal. They're in equal power in this like tug of war, right? So if you shoot past one, the acid's going to give up. If you shoot back down, the base is going to give up. Okay. I mean, you shoot up, the acid's going to be gone because the pH is now going to be, it's going to be basic. Okay. We see that here with water. So there's no buffer. So it's just going to jump from 6 pH to a little over 2. It's like 2, 2.5, 2.4, somewhere around there, because there's no pH. So the buffer allows for what? It allows for a gradual pH change. So drops without the buffer, and then with the buffer, it slowly changes. Okay, acids as the acids added and dropped. Okay. So then we can have weak acids. Before we jump into this, we have weak acid base pairs. So you could think as you add a proton or an OH group, it can stabilize the pH. Okay, so if we add more here, but this is going to make sure that it changes very slowly. Okay. Okay. Buffers are crucial in biological systems. Okay, so we're looking at the pH of blood, which I was explaining a moment ago. You'll see the conjugate acid base pair of carbonic acid and carbonate. I would definitely learn these: H2CO3, HCO3 minus. I would throw those in the bank. Okay. Um, so which one is carbonic acid? Which one's bicarb? They have it listed respectively, but H2CO3, that's carbonic acid. We got bicarb as HCO3 minus. Okay, the pH in blood is 7.4. Carbonic acid ionizes. So when a carbonic acid, let's go back to it, H2CO3, when it ionizes, it produces what? If we look at here, we see that it produces a proton. Okay, and then where does it change to? Bicarb. Bicarb, got it. Okay, so one more time. Carbonic acid, it produces a proton and bicarb. This could go back and forth, back and forth, back and forth, right? So that's conjugate acids, conjugate bases. Purpose is that they look at the transfer and acceptance of a proton, that H plus group. So I would put and I wouldn't confuse that. I'm not going to write it here, but electron would be the negative. Now we're talking about right here. Okay, conjugate acids, conjugate bases, they donate protons. Acids donate protons. They donate an H group. Bases accept protons, except the H plus group. Let's see if I can draw here. Okay, so kind of off topic, but just to drill it in, Bronsted-Lowry acid bases, they look at the transfer and acceptance of a proton. So let's say we got a Cl. Writing's be horrible, but whatever. Okay, this would be your acid. Okay, now if we add a base, let's say, oh, of course we're gonna say water, right? That's an O, H2O, right? Is it 1, 2, 3, 4? Okay, base. Okay, what's the difference here? Okay, so we notice that I should have changed colors. Oh, oh, this is the base. They should be all being blue. So the sharing, you guys see that? Okay, great. Okay, this is more so just to teach the Bronsted-Lowry acids and bases, how they transfer and accept protons. So we have an acid. Let's just put that in red. A. It's going to have acid's going to be the ones that are donating a proton. Okay. So then we'll just make this Cl. We have our electrons here. 2, 3, 4, 5, 6, 7, 8. Okay. Now we're going to add this with a water. H. 1, 2, 3, 4, 5, 6, 7, 8. Boom. Okay, this would be a forward and reversible reaction. Okay. And then we have this as your base. Probably should do that in blue, but yeah, let's do it. There we go. Zoom out a little bit. Okay, so with this, we're going to notice that this proton is going to be removed and to be plucked off and given to the base. Okay, we'll start there. We have two. But now, instead of water, we have an additional proton. Okay, right there. Okay, and then this is going to be the conjugate acid now. Okay, and then the conjugate base, Cb, make it easy, is going to be Cl, 1, 2, 3, 4, 5, 6, 7, 8. That's going to be minus. So what's the reason for me showing you this? Okay, so a strong acid is going to be a weak conjugate base. Okay, a strong base is going to be a weak conjugate acid. The base is going to have a negative charge, or it's going to be neutral with lone pairs. Okay, so these lone pairs that we're seeing, right? One lone pair, one lone pair, one lone pair, one lone pair. The forward and the reverse direction, that's where the reaction happens. Okay. Now, conjugate base is what remains from the original acid. So this Cb, it's a horrible picture. This is a horrible picture, but this is what remains from the acid, right? Okay, so since we're plucking this portion off, so I can get a shape to plucking this off, or moving it over to here, Cl's by itself. Does that make sense? Now, if we have water, H2O, now there's 3. Now it's going from a base to an acid. Okay. So the conjugate, one more time, the conjugate base is what remains from the original acid. Mm-hmm. And likewise, oops, it's going freeform. And the conjugate, this brush. Okay. The conjugate acid is what remains from the original base, okay, plus a hydrogen. This portion right here we can see. So here, this hydrogen is going right over to here. Okay, so that acid is going to carry an acidic proton as well, right here. Make sense? Okay, good. So yeah, the acids are going to give, bases are going to take. Think about them as just because this could be a forward and reverse reaction. So think about it as trading Pokemon cards, or trading Yu-Gi-Oh cards or something, right? They don't like to trade, they can go back to it. Hmm. Okay, let's go back to the normal screen. Change field. Okay, STYNQC. What's the point that I wrote this here? Does anyone have any idea? Okay, serine, threonine, tyrosine. What's the point? Okay, so STY, the amino acids, they have a free hydroxyl or an alcohol group. That's an OH. Okay, that's this right here. The hydroxyl groups can undergo chemical reactions by a nucleophilic attack. So let's look at this real quick. Um, let's see. Not be too specific, but we'll see. Wow. Okay. So we'll see here. This R group, an NH2 plus a proton, now becomes NH3. Okay. So it attacks. So when an amine lone pair reacts with any other atom other than hydrogen, it acts as a nucleophile. Okay. So you can see here, kind of going into a little bit of OChem, but that's biochem. It's gonna dance from gen chem, it's gonna dance from OChem, and it's gonna have a little dance of biology as well, even some physics as well. So um, as long as we know that that hydroxyl group, this is the OH group that's going to be in STY right here. The picture's not blurry. Here you go. Alcohol group, alcohol group, alcohol group right here. Serine, threonine, tyrosine. Also remember SER, THRT, TYR, Y. Remember tyrosine, Ty, TY, threonine. It's the only one that's you should remember that should be T. Serine, S. Okay. We also have cysteine. This is going to make disulfide bonds. Okay, the H's are going to be plucked off and it'll be SS, right? Remember that in, you went up to your, Yep, exactly. Yep, they're in tertiary. Yep. Okay, let's see, where are we at? Not too far. We got asparagine and glutamine, okay? When these are, we have a amine group, that's where you'll see N2H right here on the side, okay? Their letter is Q. So GLN-Q, glutamine. These may be the ones that mess people up with learning the three-letter groups in the one letter, and then tying it to which amino acid it is, and then what that amino acid does. Asparagine, ASN, N. Okay. And then you got glutamine, GLN, Q. Quick one for glutamine. You can hear it one time and never forget it. Glenn Quagmire from Family Guy. So GLN, Glenn, Q, Quagmire. Okay. It's glutamine. So what's the point of me going over that? So if this group right here, STN or STY, NQ, C. Okay, NQ, these will all have, so I can pull this picture up so you can see it. Exactly. Yeah. Yeah, to pull it up. Yeah, they're polar. So if you remember these as these are going to be polar. Exactly. Yeah, they're your polar R groups. Okay. Good job. You got it right here. Oh, I already had it here. Okay, perfect. STY and Q, C. Now let's not mix these ones up with aspartate, glutamate. Okay. Those ones are the negative charged R groups. Okay. Try to remember that since it ends with ene, I-N-E, that's an amine group, N2H. Whereas if it's glutamate, it's going to be a COO minus, right? That's aspartate, glutamate is going to turn to aspartic acid, glutamic acid. Okay. Make sense? Okay, here I can put a picture of, here, let's add this in here so you guys can see. Boom. So these are negatively charged R groups. I'll add these other ones as well. Awesome. Okay. HRK, remember when it's higher than 7.4, or it's at 7.4 pH. Histidines could be the one example where it's not going to be, but we're not going to go over that right now. But it's going to be deprotonated, so they're going to have an extra proton. Okay. Negative, it's going to be different. Okay, just touch on this portion just to dial it in a little bit more. So these amino acids, serine, threonine, tyrosine, TYR, or STY, the reason I brought them up again is that they can be phosphorylated. Okay, they're the one amino acids that can be phosphorylated. So this is their R group. Okay, you have a picture of it underneath it. Yeah, this is their R group. This is OH here. As a site where a phosphate group can be attached. Okay, it removes that H group. Boom, phosphate. This is the end of tyrosine. This is the R group, the amino. Boom. Okay. And then I threw in some little notes just in case anyone was curious for anything past this class. There's aspartate or glutamate, which were these that we are going with the negatively charged. They can act as a site for phosphorylation. They can mimic a phosphate. Okay, so if you replace a phosphate group with an aspartic acid, um, this would be a site of phosphorylation. If you replace that phosphate group with aspartic acid or glutamate acid, you can see that it can become permanently activated. That would completely change. That's called a phosphomimic effect. It would permanently turn that on. Okay, whereas let's say if it was a serine, a threonine, or tyrosine, it's not permanent. But once that's on with aspartic acid or glutamic acid, because they're going to be attached, right? It's not going to just unbind from here. It's going to be permanently phosphorylated. So it's going to be an on switch for whatever metabolic process that's doing. Okay, get next portion for you guys here. Okay, any questions with that? Okay, yeah, so mhm. So serine, threonine, tyrosine, their alcohol group, the hydroxyl group, it could be a site for a phosphorylation. Okay. So the target for a phosphorylation is adding a phosphate group to them. Let's not have that be confused with a kinase enzyme. A kinase enzyme adds a phosphate group, so that makes it phosphorylated. That's where knowing these terms very well can get you so you don't get tripped up. You don't get confused. Because the wording on this can be a little tricky. Where a phosphatase, we know our enzymes, phosphatase, it removes a phosphate group. Okay, that makes them unphosphorylated. Okay, you'd see that in hmm, can't think of any off the top of my head where we'd use a phosphatase. A kinase, that would just be anything that, yeah, it would be anything that would just add a phosphate group to it. So glycogen synthase, there's some other cascade effects. Maybe you would see that more in a some kind of a mutant gene or some kind of experiment where you would use a phosphate group. Off the top of my head, I can't think of any phosphatases. Okay. Yeah, no, good questions, of course. So we got essential amino acids. We just got a few more minutes left. We'll wrap it up. Essential amino acids versus non-essential. I highlighted the essential in yellow. So valine, and I would keep a printout of this. I'd keep a printout of this. So you got valine, histidine, lysine, leucine, isoleucine, methionine, threonine, phenylalanine, tryptophan. Okay, I would pause for a second and think, how can we group these together? Because we already have our groups we're trying to memorize, our polar groups, our non-polar groups, positive, negatively charged, our groups. They have a aromatic ring. how they react. They can be phosphorylated if they have an OH group, a hydroxyl group. We have so many things we have to learn for amino acids, and that's not scratching the surface. That's a good majority of it, but there's still a lot more. We have a proline that'll cause the kinks and foldings. We have, let's see what else we have. We have our negatively charged groups, aspartate, which is really aspartic acid. We have our negative charge group, glutamate as well. Hmm. Yeah, yeah. So just try to break it up. So our non-essential, you can remember either one of these. You have to remember both of them, but whichever one sticks to you the most. Um, and just know that if you're asked a question, okay, is this essential or is this non-essential? Then remember this mnemonic, and then you can trigger back to it and go, okay, well, it's not one of these, so it's got to be the opposite. Okay, so any amino acid that starts with an A, C, or G, that's going to be a non-essential. We have proline, serine, and tyrosine in that group as well. So if we remember ACG, and then pop star Taylor Swift. So P for proline, Taylor, T, tyrosine, and also and serine for Swift. Okay, that one doesn't stick to you. Maybe you might remember it in 10 years out of nowhere. Um, you can remember like George Clooney, Pamela Anderson, Taylor Swift, just the first letters. But you have to remember that A, C, and G, it's every amino acid that starts with an A, C, or G. So it might be a little easier to remember the non-essentials. You just remember every amino acid starts with an A, C, or G. And then there's proline, serine, and tyrosine. However you want to remember those, that's fine. The essential amino acids, it's a little easier. It's VH, MLK, WTF. Okay. Very hungry, milk, WTF. Super simple. Okay. Here's your list. Give you a moment to take a screenshot, make your notes. Okay. Non-essential, get alanine, see all the A's, C, G. There's no A, C, or G on this side. Let's start with them. Yes, let's start with them. That's correct. Okay, you have proline, serine, tyrosine, Taylor Swift, Pamela Anderson, or however, anything with a P. Right. Okay. So last question before we head out. Leave you guys at this, give you a few minutes. So strong acids, and we went over this for quite a bit. So strong acids and bases, they do what? Weak acids and bases, they do what? Acids, they do what? Bases, they do what? Yeah, these are your answer choices below. So you just pick one and pluck. Mhm. Okay, so let's start with our acids. We'll go the one the middle. So acids, it's remember they are proton donors. Okay, so let's see if we can annotate on this because we're gonna get rid of it after. So P D proton donors. We can cross that out. Okay. Bases are proton acceptors. Okay. Good job. So what do weak acids and bases do? Do they completely ionize in dissolved water? Mhm. Yeah, they do not. And we can process of elimination is strong. It's probably going to completely ionize. Yeah, keep it very simple. So if it's strong acids and bases, they completely ionize. If it's a weak base, it's not going to completely ionize. Good job. Mhm. So strong acids, they're going to completely ionize in a dilute aqueous solution. So think about it as an acid is going to be a proton donor. So it gives a proton, an H plus. Okay. Now if it gives away a proton, makes it an acid. Okay. So it's just think about it as just someone that's there to pay for your lunch or so. A base is someone that is saying, "Hey, I'll take that free lunch." They're the one that wants to take the proton. And then remember, when it swaps, once it accepts that proton, it swaps over. Okay. So the forward reaction, the acid donates, the base accepts. Reverse, the conjugate acid and the conjugate base, they swap roles. Okay. So you'll see that the acid goes to the conjugate base after donating a proton. Base goes to a conjugate acid after accepting a proton. Yeah, it goes back and forth. Okay. Yep. Just think about it as they're at a tournament playing Yu-Gi-Oh. They trading cards. They go, I want to take it back. Okay. But in this case, someone is giving away a Yu-Gi-Oh card, and then they're letting someone borrow it. So not really trading Yu-Gi-Oh. Well, kind of trading. But I would like to think of it as for the yeah, exactly for protons. So they're giving a Yu-Gi-Oh card, and then they get it back later if they decide to go back in the reaction. Okay. Cool, guys. Well, good luck with your midterms. Yeah, have a good one.